Here's an application of the intermediate value theorem that I'm very fond of. Here's how it goes. Suppose you got a function f. F is continuous in the closed interval between 0 and 1. And whenever x is between 0 and 1, f of x is between 0 and 1. So that's what you got to suppose. What do you get out of this? Then there is a point x between 0 and 1, and f of x equals x. It's telling you that there exists an input so that if you apply f to that input value, you get the output, which is the same as the thing you plugged in. You call these things fixed points. So you imagine that f is moving around the points between 0 and 1, and you're finding a point x which doesn't move, a fixed point. Why is something like this true? Let's see. I'm going to use the intermediate value theorem, but I'm not going to apply the intermediate value theorem to f. I'm going to make up a new function, g of x equals f of x minus x. What do I know about g? G is continuous. F is continuous by assumption. The identity function x is continuous. And differences of continuous functions are continuous. So g is a continuous function on the closed interval 0, 1. I also know something about the values of g. What's g of 0? Well, g of 0 is by definition f of 0 minus 0. F of 0 is between 0 and 1. So I've got a number between 0 and 1 minus 0. That number is at least 0. I also know something about g of 1. G of 1 is by definition f of 1 minus 1. F of 1 is between 0 and 1. It could be 0, could be 1. But a number between 0 and 1 minus 1 is less than or equal to 0. What do I know altogether? I've got a continuous function g. Its value at 0 is bigger than or equal to 0. Its value at 1 is less than or equal to 0. By the intermediate value theorem, this gives me a point x so that g of x is equal to 0. Why do I care about finding a point x so that g of x is equal to 0? Well, if I take a look at what g of x is equal to, g of x is f of x minus x. So I found a point x so that f of x minus x is equal to 0. I found a point x so that f of x equals x. I found the fixed point. So we've seen why this is true. Let's try to apply this to a specific example, like f of x equals cosine x. Now here I've got a graph of cosine. Here I've got the graph of y equals cosine x. Now what do I know about cosine? I know cosine's continuous, and cosine of a number between 0 and 1 is a number between 0 and 1. So our statement applies to it. There's a fixed point for cosine. There's some value of x between 0 and 1, so cosine of x equals x. Let's see if we can find that on the computer. Okay, I've got cosine loaded up on my computer. Cosine of 1 is about 0.54. Let me decrease the input. Now notice that cosine of 0.68 is 0.77. Here, the input is smaller than the output. Let me increase the input. Now, notice what happened. Now the input is 0.74, but the output is smaller than 0.74. Cosine of 0.74 is just 0.73. Now I'll decrease the input. Ooh, the opposite thing happened. Now the input is smaller than the output. Now I'll increase the input. I'll decrease the input. Increase the input. And you can see that I can sort of zoom in or narrow in on the correct value of x so that cosine of x is equal to x. So using the computer, I found that this point here is at about 0.739. So we found a number between 0 and 1. Cosine of that number is itself. It's a fixed point for cosine. These kinds of fixed point theorems, statements that assert the existence of fixed points, they pervade mathematics. Here's another example. I've got a map of Ohio right here. Let me apply a continuous function to this map. I'm going to throw it down to the ground, stomp on it, and now let's take a look at it. Now the question is there a point on the map which is exactly above its corresponding point in the ground? And indeed there is. I'll use this pin to stab through that point.